Okay, welcome. I hope everybody's having a good day today. Today, we're going to be talking about application of AC circuits, and we're specifically going to be looking at RC series circuits. So we're going to be looking at circuits which have a sinusoidal source and a resistor and a capacitor that are in a series configuration. So let's take a look at what we're talking about. This is a typical RC series circuit, and this is what it looks like. We start out with a source, and we assume that the value of the voltage on the source is an RMS value unless indicated otherwise. So if we just write E sub t for E total, and let's just say that that's 120 volts, we're talking about an RMS voltage, okay? And now, to move away from just dealing with low voltage power circuits, let's designate the frequency of our circuit to be operating at 1.2 kilohertz, which of course would be 1,200 cycles per second, or hertz. And then connected to our AC source is going to be a resistor and a capacitor. So we'll label our resistor R sub 1, our capacitor C sub 1. And what we're going to do is we're going to give values to the resistor and the capacitor. Now, if you remember last time, we talked about how we make a conversion from the unit of farads to the unit of ohms. And if you recall, we said that X sub C, which is capacitive reactance, in other words, that is the opposition to current flow that the capacitor offers to a DC signal. Capacitive reactance is equal to 1 over 2 pi times the frequency of the source, in this case 1200, times the energy storage rating of the capacitor in farads. Okay? And so let's just say that when we plug those numbers in, we ended up with a capacitive reactance of 320 ohms. So we're going to say that the capacitive reactance of this capacitor is going to be 320 ohms. And the resistance is going to be 120 ohms. Now, one of the things that we talked about last time, and I want to emphasize this time, is that the current and the voltage are not in phase with each other in an RC series circuit. I'll repeat that. The current and the voltage are not in phase with each other. Now, there are two different ways to look at that. If we looked at that over to the right here on the display of an oscilloscope, which would show us a plot of time versus voltage or current, we would see our voltage signal, let's say this was the dotted line, was the voltage, and then the current signal would cross through 0 at a different time. These 0 crossover displacements constitute a phase difference. This right here is what we call a phase difference. And so we call that by an angle that we named theta, which is just named after a Greek symbol, theta, theta. And the fact that the voltage and the current don't cross through 0 at the same moment in time is what makes an RC circuit unique with respect to a circuit that only has resistance in it. A circuit that only has resistance in it, remember this is an RC series circuit, a circuit that only has resistance in it, if we plot time versus voltage or current, we would see this kind of a phenomenon going on. The current would always cross through the 0 crossover point at the same time. So every time we look for a 0 crossover, we would notice that the current, which is represented by the solid line, and the voltage, which is represented by the dotted line, they cross over through the time axis at 0 at the same moment, which means that there is no phase displacement or there is no phase shift in the circuit. Now, this is all fine and dandy, but a little bit difficult to analyze. So what we're going to do is we're going to use what we call vector analysis to analyze the circuit that I proposed initially. So let me erase this. Let me just quickly redraw our circuit. So if you recall, our circuit has a 120 volt source at 1,200 cycles per second, and there is a resistor and a capacitor connected in series to each other. The resistor has 120 ohms of opposition to current flow. The capacitive reactance of the circuit, this is the resistance, this is the capacitive reactance, we said was 320 ohms. Okay, so now we have the unit on both resistance and capacitive reactance measured in ohms. So now we're dealing oranges with oranges, not oranges with limes. Okay? Now, if we want to solve for different things in this circuit, one of the first acronyms that I like to point out to folks, which you'll read in the book, is the acronym Eli the Iceman. E-L-I-I-C-E. Eli the Iceman is a way to remember, if you're dealing with an AC circuit, what's leading and what's lagging. If you use this method, it'll make it very simple. If you don't use this method, it'll seem convoluted and you'll probably never really fully understand it. If we have a circuit that has a capacitor in the circuit, okay, if it's an ideal capacitor, then the current is going to lead the voltage by 90 degrees. If we have an ideal inductor in the circuit, which we're not talking about tonight, but we will later, if we have an ideal inductor in the circuit, then just the opposite. The voltage will lead the current by 90 degrees. So that's kind of a slick little way to remember what's in front and what's behind, what's leading, what's lagging. Okay. L stands for inductance. Okay, and we haven't really studied that yet, but when we memorize the acronym to identify what's leading and what's lagging in a capacitor, if we leave out the Eli part, then it's hard to memorize the acronym because it's Eli the Iceman. So rather than just giving you ice, I'm giving you Eli too, okay? All right. Now, it turns out that because the current and the voltage are 90 degrees out of phase with each other, right, then it turns out that also the voltages, if we were to measure the voltage across this capacitor and the voltage across this resistor, are also going to be out of phase with each other, okay? And so one of the things that we do is we develop what we call vector diagrams. Vector diagrams, okay? And there's a vector diagram to go along with just about anything that you want to analyze in the circuit. Like, for instance, let's say we want to analyze voltage. Somebody asked us, how do we determine what the voltage drop is going to be across the capacitor and across the resistor, given the fact that we have a phase shift in the circuit? Well, we simply draw a right triangle. And in the right triangle, the horizontal axis is going to represent the voltage drop across the resistor, okay? The vertical axis, which I'll actually be drawing in a downward direction when we deal with LRC circuits, but for now I'll just draw it upward. It's easier to learn that way. Will represent the voltage drop across the capacitor. And can anybody guess what the hypotenuse will represent? It'll represent the voltage drop across the source. Or, if we started out with an impedance diagram, which would represent the opposition to current flow of each one of the items in the circuit, we could do that. So let's just go along with what was stated there. Let's say that our hypotenuse was going to be the total opposition to current flow seen looking out from the source, or the impedance of the whole load. Okay? Then the horizontal component of this impedance vector diagram would be the resistance. And since we only have one resistor in there, we know that's 120 ohms. Okay? Anybody have a guess what the vertical component of this right triangle would be? Right. It would be the capacitive reactance in the circuit. So it would be X of C, which is the capacitive reactance in the circuit, and that's 320 ohms. Okay? So using the Pythagorean theorem, knowing that this is a right triangle, we could then easily calculate what the total opposition to current flow is for the circuit, or the length of the hypotenuse. So Z would be equal to the square root of R squared plus X of C squared, or 120 quantity squared plus 320 quantity squared. So why don't you put that in your calculator and tell me what you get when you take the square root of the sum of these squares. Okay, I'm getting approximately 341 ohms. Is anybody else getting that? 341? Okay, so what that tells us is that we could redraw this circuit, okay, as the same source, which has 120 volts, connected to a box. And the box would be the impedance, or the total opposition to current flow in the circuit. Okay? And what we found was that that impedance was approximately 341 ohms. Now, if we know what the total opposition to current flow is for the whole circuit, and we know what the voltage is at the source, right, then Kirchhoff's voltage law tells us that the sum of the voltage drops around any closed loop must be equal to 0, or, more simply stated, if there are only two items in the closed loop, they must have the same voltage. Okay? So this impedance right here has a voltage drop of 120 volts, which makes it simple for us to figure out the current that's flowing in this circuit, or the current flowing from the source, by using Ohm's law. The total current is equal to the source voltage divided by the total number of ohms for the circuit, or the total impedance of the circuit. So that's going to be equal to 120 volts divided by 341 ohms. And so what do we get for the amperage in that circuit? 0.353. Okay, so there's 0.353 amps, or 353 milliamps. Now, if the current is 0.353 amps here, and we move back to our original circuit, what must the current be in that circuit if they're equivalent circuits? It's got to be the same, right? So we're going to draw the current here is 0.353 amps. Fix that. Okay. Now, the one thing that is not affected by the fact that we have components that are out of phase with each other is a circuit where we have two components in series. Because when components are in series, we know that the current does what through those components? It's always the same. In a series circuit, whether it's AC or DC, the current is always going to be the same through every component because there's no branch. There's no place for it to branch out. Okay, so let's work backwards for a moment, and let's use Ohm's law to figure out what the voltage drop across the capacitive reactance would be, number one. Okay, so I'll just just make a little separation here. So the voltage drop across X of C would be equal to, voltage is equal to what? Current times resistance or impedance. So it would be the current multiplied by Z, which would be equal to 0.353 amps multiplied by 341 ohms. So what do we get for a voltage drop across the capacitor?
120 million volts.
So when you take 341 and you multiply it by 0.353, what do we get?
Yeah, you get
120.4 volts. Okay, so we're getting a drop of 120.4 volts here. What about the voltage drop across the resistor? That's going to be equal to the current flowing in the whole circuit times the resistance, which is going to be equal to 0.353 multiplied by 120. What is that now?
2.4.
So that's equal to 32.4. And that's going to be volts. Now, one thing that I want you to notice, okay, which is very important in this, is that when we come back to this original circuit right here, and we look at Kirchhoff's voltage law around the closed loop, it still applies, okay? But there's a difference between analyzing DC circuits and analyzing AC circuits. And the difference is that the voltage does not add up algebraically. It adds up vectorially, okay? So let's talk for just a moment about the difference between a scalar Oh, did we make a... What number did you get?
Your last calculation is 42.36 instead of 34.
42.36. Okay, I'm counting on you guys. 40 what?
42.4.
42.4. And then did you double check this one?
Yeah.
0.353 times 341 is 120.4. Okay. Now, we need to talk about this for a second before we actually implement this, okay, just to make sure everybody's clear on it. Can somebody give me an example of a scalar quantity? Well, I'll give you one. How about counting money? If I count out $20 to you in $1 bills, okay, then basically, if I were to say something to you like, I owe you $20, I've got it in $1 bills, I'm going to count it out to you right here, right? Or I'm going to count it out to you right over here. There's no difference, right? It doesn't matter whether you're standing on my left, you're standing on my right. There's no direction associated with the process of counting money, okay? There's really also no direction associated with temperature. In other words, if I said 73 degrees in Los Osos, and you're on the cell phone with me and you say, well, it's 81 degrees in downtown Slow, okay? And I said, well, can you be more accurate? Well, what I'd really be looking for is, you know, is it 81.1 or is it 80.9? But if you said to me, well, it's 81 degrees bearing north-northeast, that really wouldn't make any sense, right? Because we don't attach direction to temperature. And so temperature is what we call a scalar quantity. The best vector quantity that I can think of is velocity. Let me spell that right. How do you spell velocity? V-E-L-O-C-I-T-Y. Velocity. So velocity is like, you think of an airplane. Airplane might be flying at 500 miles per hour, but it's very important what direction it's flying. Because if there's another airplane flying, you know, directly toward it, then they're going to collide with each other, and neither airplane is going to be flying, okay? So velocity is a quantity that has a magnitude, in other words, how fast are you going, how many knots, how many miles per hour, and also a direction. What direction are you headed? What's your altitude? Okay, so there's more things involved than just how big is it. Okay, we also have to worry about what direction we're headed. Okay, so coming back to this circuit right here, it turns out that when we were analyzing DC circuits, if we were to write Kirchhoff's voltage law, we would say that the source voltage is equal to the voltage drop across resistor 1 plus the voltage drop across the capacitor. Okay? And we would add them algebraically. 5 plus 5 is 10. 10 plus 10 is 20. 20 plus 20 is 40. That's adding algebraically. When we're dealing with RC circuits where we have an out-of-phase condition, which we see on the oscilloscope that I erased, but I drew in the beginning of the lecture, okay? These have to be considered as what we call vector quantities. And by putting a little arrow over them, we designate the difference between a quantity being a scalar and a quantity being a vector. So basically what the Kirchhoff's voltage law still applies, but what it says is that the total voltage is equal to the voltage across the resistor plus the voltage across the capacitor. Now notice something interesting. Kirchhoff's voltage law says that this voltage must be equal to this voltage plus this voltage. Okay? But we're not adding them algebraically. We're adding them vectorially. So back to my vector diagram, if I get away from my impedance vector diagram and I replace that with a voltage vector diagram, I find that the voltage that I measured across my capacitor was 120.4 volts. The voltage across the resistor was 42.4 volts. And so how would I figure out what the voltage across the source is, which is the length of the hypotenuse? I would use the Pythagorean theorem. So I would take the square root of 120 squared plus 42 squared, and what would I get?
They don't put the decimals in there. I got 127 with the decimals.
Okay. Well, that's fine. I mean, so you can see that that's approximately 120 volts. Now, if we carried the decimals all the way out, we would find it would be exactly 120 volts because that's what we started with, and that's what generated our current. But notice something very interesting here. We have 120 here, and we have 40 here, and this is only 120, right? The reason is because we're doing vector addition. We're not doing scalar addition. If we were doing scalar addition, this would be 120 plus 42, that'd be 162, right? So what you find is that when you're measuring voltages in an AC system, you can't use Kirchhoff's voltage law the way that you've been accustomed to using it in DC analysis. In other words, if you come with a voltmeter and you measure the voltage here and you write it down, and then you measure the voltage here and you write it down, you can't just add them together to get the voltage that you'd measure here. It seems at first glance to surpass or not comply with Kirchhoff's voltage law. But it does in fact comply with Kirchhoff's voltage law because we have to use the Pythagorean theorem to add the voltages together. Okay? So we call this a vector voltage diagram. The horizontal component representing the voltage drop across the resistor. the vertical component representing the voltage drop across the reactance. And in this case, it's a capacitive reactance. And then the hypotenuse representing the voltage drop, or the voltage that we would measure if we went right to the source. Okay? Any questions? Okay, now, the only thing that is not going to be defined with a vector diagram is going to be the current. And the reason is because we have a series circuit. And by definition, in a series circuit, the current is what? Always the same. So if we wanted to, we could generate a vector diagram, but it would look like this. This would be the current flowing in the resistor. This would be the current flowing in the capacitor. And this would be the current flowing at the source. In other words, they're all the same. So if you want to draw an arrow, you can, but it's not necessary because they're all the same in magnitude and direction. Okay? Anything except for current, you're going to have to draw a right triangle, and you're going to have to analyze it using the Pythagorean theorem and the basic trig concepts that we learned about. Any questions? They're not real difficult to analyze. You can analyze impedance with an impedance diagram. You can analyze voltage with a voltage vector diagram. You can analyze current, and you find that the current's all the same, even if you try to draw a vector diagram, just if you know the definition of a series circuit. You can analyze power factor or power flow through the circuit. And let's talk just very briefly about that. I'll erase my vector voltage diagram, and let's talk about a vector power diagram. Okay? In a power diagram, when we're talking about only power, it turns out that there's 3 different types of power that flow in a circuit that has resistance and reactance in it. Okay? There's what we call power true, or sometimes power real. Sometimes we call it power real, and that's always measured in watts. Okay? And then at a 90-degree angle relative to the watts, we find power reactive. So this is power reactive, and that's measured in the unit of VARs. Anybody know what VARs stand for? Volt amperes reactive. Volt amperes reactive. So the power that is dissipated in the resistor is indicated by a horizontal arrow in a vector diagram and has the unit of watts. The power that's dissipated in the capacitance is what we call wattless power. In other words, the power at one moment is being absorbed by the capacitor as the capacitor is charging, and then being delivered back to the source as the capacitor is discharging. So it's like a teeter-totter. You know, at one moment you're pushing up, and at another moment you're falling down, and you just kind of teeter-totter back and forth. And that's what the power in the capacitor does, and we call that wattless power because an ideal capacitor dissipates no heat. A real capacitor dissipates some heat because there's actually resistance in a real capacitor. But an ideal capacitor, which is what we model in our circuits, dissipates no heat and is measured in volt amperes reactive. And then finally, our power triangle has to end with the power that is absorbed at the source. We call this power apparent. Power apparent. So that's the apparent power. And the units that apparent power is measured in is volt amperes. Okay? So what you would find is that if you knew the power that was absorbed here, and you knew the power that was absorbed here, you couldn't just use superposition and add them algebraically to figure out the power that was being delivered here. Because this plus this algebraically does not equal the length of the hypotenuse. You would have to use the Pythagorean theorem, or the square root of the true power squared plus the reactive power squared would give you the apparent power, which is the power that the source is delivering. Okay? Any questions about that? Okay. All right, so in your text, you'll see that there are a couple of examples where they draw a power triangle and they show you how to calculate them, and they do it for you. And then in your practice problems, there are some additional problems. But again, you're just using the Pythagorean theorem, c squared equals a squared plus b squared, right? And then later, we'll be dealing with the angles inside the triangle. This angle right here, we call theta. And this angle right here, we call phi. Okay? And we find those by, anybody remember the acronym to find the angles? SOHCAHTOA. Right, SOHCAHTOA. Okay? All right, so if there are no further questions, then that'll end our lecture on series RC circuits. And I hope everybody has a good night.